Intel Battle Mage for AI use cases. Intel Arc Pro B60. 24, 48, 96 gigabytes of VRAM sitting right here. This is, of course, Battle Matrix. And I need your help. Yes, you there, watching the video. We have a lot to discuss about Battle Matrix. I enjoy this because these cards have an ordinary 8-pin connector, just a single 8-pin connector on the end of the card. Now these are the 24 gig version. There is a 48 gig version of these GPUs. It's not really 48 gigs, it's two 24 gig GPUs on one card. So you could pack in 8 of these in 4 slots. For us, we're gonna do 4 in 4 slots. Well, 4 in 4 double slots. But that'll work in an ordinary desktop computer with an ordinary North American power outlet. 15 amps, 120 volts, because it's what we're rocking here in North America. These Sparkle Arc Pro cards, in addition to the normal 8-pin power connector, have 4 DisplayPort connections, a PCIe Gen 5 X8 interface, and flow-through design, which is actually important when you're packing in this many GPUs. It makes it a little easier to deal with. So let's get our Intel Xeon host system. This machine is Battle Matrix. It's a Xeon 3435X, 8 memory channels, 16 cores, and that matters because if you're going to hang 4 GPUs off of a workstation and actually feed them, you don't want a platform that collapses under its own weight. You need a lot of I/O. But it's interesting because the CPUs are not doing the heavy lifting here. I mean, this is basically Intel's Xeon reference platform, and this is pretty much what you need to drive 4 of these GPUs. Each one of these, 20 Xe cores, 5 render slices, 160 XMX engines, 192-bit GDDR6, 24 gigs of VRAM. There's 8 lanes of PCIe Gen 5 for connectivity. Together, these 4 GPUs have 96 gigs of VRAM, as much as an NVIDIA RTX Pro 6000, which costs $8,500. But the 4 of these GPUs costs about the same as a 32 gig RTX 5090. So this is the part that people keep missing, I think, about the B60. It's not trying to be the biggest, baddest data center GPU ever, or even workstation GPU, but VRAM per dollar, and VRAM per dollar that speaks modern AI. So that you can have this workstation power with a relatively modest power envelope, because each one of the GPUs, is only on the order of about 150 to 200 watts. There's some variability in that with board partners, but Sparkle's doing a good job here. Intel's dedicated matrix hardware, there is XMX. Intel's positioning with that, I think, is run it locally. Intel is leaning pretty hard into the Int 8 throughput, though, 197 TOPS per card. And the practical story is if your model fits in VRAM and your kernel path is Int 8 compatible, you should have a pretty good experience with this platform. 456 gigabytes per second of bandwidth per GPU. It's one of the quiet headline specs. And 8 lanes of PCIe Gen 5 is a lot of bandwidth. For data parallel workloads that don't need constant cross-GPU chatter, you'll be fine. For tensor parallel workloads that do need synchronization traffic, PCIe maybe becomes a little bit more of the story, but keep in mind you still have as much bandwidth as 16 lanes of Gen 4. And if you're doing pro workflows, it's not just for AI. You've also got ray tracing hardware and modern graphics APIs, and the media block with the dual codec engines. I think this might deserve its own separate investigation apart from the AI and Battle Matrix that's the focus of this video. So, 24 gigs of VRAM per card, decent Gen 5 bandwidth, XMX for AI kernels, and Pro Media workstation features. That's the baseline for this platform before we even touch the benchmarks. So keep that in mind. Just level setting expectations here. It's like, oh, it's not as fast as an RTX Pro 6000. Let's talk about strategy, because Intel's fighting for AI market share, and not from the high ground. NVIDIA owns mindshare. AMD has real momentum at the highest end in the enterprise, and they're starting to have a credible workstation and server story. So Intel, their angle with Battle Matrix is different. Validated full stack for people who want local inference, local workstation type tasks. Intel's own description is basically codename Battle Matrix for an all-in-one inferencing platform combining validated hardware and software, aimed at privacy-conscious pros who want to avoid subscription costs. Okay, I mean, yeah, don't we all? Intel literally says on their public battle matrix webpage, yes, this could be your taking off point. Up to 192 gigs of VRAM, that's on the dual card version of that for 4 physical cards, but two GPUs per card, and a workstation experience, and a first-class Linux workstation experience. Intel's pitch will fail if the software part of it fails. And historically, Intel has been a software juggernaut. But 2026, moving fast, mainline versus vendor branch. I'm looking at VLLM here. Mainline VLLM is at 0.15 at the time that I'm doing this video, released December 18th, 2025. Intel's LLM stack on this that shipped in December was a little behind that. As of January, it's 11.1, so it's a little behind. Yes, Intel is maintaining cadence, but there's still a gap versus mainline VLLM. And whether that gap matters or not depends on whether or not you need the latest features right now, or you want something stable that's going to ship with known good drivers and kernels. Intel is leaning on known good drivers testing. The target OS here, though, is Ubuntu 25.04, kernel 6.14. I was a little surprised it's Ubuntu 25.04, but I'll take it. The VLLM difference also means that I have to be a little bit careful here. When NVIDIA shipped Blackwell, a lot of the optimized software wasn't in place yet for Blackwell. I'm not ready to do a full comparison because I'd like to try to control VLLM versions, but I'd also like to use a version of VLLM that has been properly optimized for Blackwell. I don't want to accidentally compare and contrast, like, okay, this is the Blackwell performance that we can expect. We're using an older VLLM when that older version of VLLM lacks the Blackwell optimizations. You see, it's a little tough for me here. So if your workflow is to serve a model, you're going to be fine. It's pretty great. But if your workflow is to fine tune and mess around with the stack, I mean, there were certain problems with W8A8 implementation support and LLM compressor. I don't know. For diffusion and attention heavy runs, you may see bandwidth ceilings before compute ceilings. We can experiment with this with resolution and context length, but let's do a quick run through of the low hanging fruit, the benchmarking that I can do with those caveats. All right. Benchmarking battle matrix. It's a little challenging because of the VLLM version. First off, MX FP4, that is definitely the best foot forward with this platform. Both the 120 billion parameter model requiring 60 gigs of VRAM and the 20 billion parameter model. 120B runs great on a 4 GPU setup because you have all that extra room for lots of Vcache. And also if you're tempted, it's like, oh, I could run this on 3 GPUs. This is not a thing. This is not a thing pretty much universally. You can have tensor parallelism of 2 or 4. 3 is right out, just like in Monty Python. So the performance and the benchmarks, I've collected all of that and I've put it in a thread on the forum. And that's really where you should go if you're interested in the nuts and bolts of it. This is YouTube. It's video. This is for me to wax poetic and get everything mixed up and blah, blah, blah. The ground truth is there in the forum thread. So check out the forum thread. GPT OSS 120B running the VLLM serve benchmark. 51,000 tokens input, generated 25,000 tokens, 3.9 thousand milliseconds, or 3.9 seconds to the time to first response. On a 120 billion parameter model, this is pretty good, and 986 tokens per second. But I also use OpenWebUI, and so using OpenWebUI is, okay, how are you going to use it interactively with a UI? And that's this. And I just hit the drop down and pick different models. I'm testing Qwen here instead of GPT OSS 120B, Qwen 3, 30 billion. And it's like, oh, hello. And it's like, please write an efficient Python program for searching for perfect numbers and then watching the result and seeing how that goes. And generally, it does pretty well. If we go through the tasks here, everything was basically going according to plan. I encountered some problems with Llama 70B. It's like, all right, Meta Llama 70B. This is an FP16 model. So even though it's 70 billion parameters, the ground truth model from Meta is 70B, 70 billion parameters of FP16, so 140 gigabytes of VRAM. That's not going to run here. But Intel does support dynamic quants. You see, you need to live and die by the GitHub repository that Intel has for LLM Scalar. That's their fork of VLLM. It's, a slightly older version, and so they paper over the fact that it's a slightly older version of VLLM. But the README is very good, and it has green check marks for all of the models that you would think that you want to run. And they also have helpful hints and notes. VLLM MLA disable if you're going to run the DeepSeek V2 Lite. Okay, but FP16, Dynamic Online FP8, Dynamic Online Int4, and MX FP4. Now the GPT OSS MXFP4, but these cards show how strong they are with MXFP4 IMHO. And so maybe other quants that other people are doing, your mileage may vary. Maybe you can get into some fun quants from Unsloth and get some pretty good performance here. But this is kind of the sandbox that you have to stick to at this point with the work that Intel has done in order to make this operate. I was really excited for a second with like GLM. I was like, oh, I'll be able to run GLM 4.5. GLM 4.5 is too big. You'd have to run like a really tiny version of it in order to get it to fit with this. But Quinn and Whisper and the 8 to 20 billion parameter models, oh yeah, all day long it's going to work pretty well on this platform. So what was my trouble with Llama 70B? Well, I got unsupported D-type, and this is because I needed to run the command to do a block size of 64. I did not explicitly say block size 64. The other thing that confused me for a second was VLLM use v1 equal 1. Like when troubleshooting this kind of D-type error, it's like, oh, I should probably turn v1 off. But v1 is designed only to use chunked stuff, and that's commentary. That's a VLLM thing. That doesn't have anything to do with Intel. But I was trying to troubleshoot why it was telling me that. So something about the block size. With that running, this is the performance that I got immediately, which is also not the best performance you can actually get out of Llama 70B, but I'll come back to that in a second. So I was like, okay, that's a little worried about the 30 seconds time to first token, but these random tests are kind of challenging. So I hooked it up to OpenWebUI, and I got this error. It's like, oh, as of Transformers v4.4, you need a chat template, and it's like, but the JINGA chat template's not part of Meta's repository. So I created this one and ran it, and it mostly worked, but it was also a little bit incoherent. So if you want to do that, this is the exact command that I used here, so you could recreate what I did or mock me derisively in the comments for something that I did wrong. But with that, we're getting about 20 tokens per second output. And this is running Llama 70B, the FP16 model, but in a dynamic FP8 quant. So it's sort of doing this on the fly. Now, the best case scenario for Llama 70B is this. It's about 12.9 seconds time to first token and about 366 outputs, tokens per second, in your absolute best case scenario with Llama 70B in this kind of a scenario. So Qwen 330B, again, that's a much smaller model. This is the exact command that I ran. This is the performance that I got for that, and that is a throughput of 991 tokens per second. And I think that you'll want to follow this thread because there'll probably be follow-ups that are like, oh, there's a new version of VLLM from Intel, or oh, instead of block size 64, use a smaller block size, and your tokens per second and your output will go up a little bit, or your prompt processing will improve. I also did the DeepSeek Distill Llama 70B, which again is another Llama 70B model, and so this should work just the same as Llama 70B model. But the reality is that the distillation works much better, and so this again was on the order of 178 tokens per second, total token throughput 536, and the mean time to first token was 43.8 seconds, but again, long prompt, and the actual WebUI results were much more coherent. So this parallelizes really well, but I can also tell you that in OpenWebUI, the time to first token for my prompt, which was very short, write a Python program to search for perfect numbers, there's not a lot of tokens there in that prompt, and the time for first token here was a second or two. Now, there is a place where that is the time to first token benchmark numbers are a little bit of a warning, and that is when you're using agentic coding. So if you're using an editor that is going to load a lot of context, like say 10,000 tokens of context, that is when the pre-fill performance will bite you a little bit. And we talk about that a little bit in this thread. I also talk a little bit more about the no chunked pre-fill and how that can sometimes, how some of the things that lead to that. While I was doing this testing, I also managed to crash the GPU kernel. So I put together a little script here to help you diagnose when a GPU is down. This could actually be added to, like we did the HA proxy video, you should check that out. This could be added to a health check on HA proxy, which could send you an email when a GPU crashes like this. This is not necessarily an Intel thing. I have this problem with Blackwell GPUs. I have this problem pretty much with any systems that I'm administering that have more than like a couple of GPUs in them. Like something will happen and the GPU will drop. And so you can put together a little script to make it part of your HA proxy or make it part of your availability proxy to just check and be like, oh, one of the GPUs is down. I should email an administrator because we're probably going to need to reboot, or we're probably going to need to do something to get that GPU back. And then there's the exact commands that I ran for the DeepSeek distill configuration and all of the other stuff that goes with that. So there's some discussion. There's good discussion to be had on the forum. But for the first volley from Intel and for how they're structuring their development here and how organized they are and how everything is happening in the open on GitHub, good results there. I want to see better time to first token, and I want to see better performance when we are doing agentic type coding, or if you're using an editor that needs a lot of context. I want to see these GPUs process that really quickly. And I don't know if that's prefill. I don't know where the improvement needs to be made. But the end user experience, like, all right, I don't care about the nuts and bolts. I just want to get up and running with this quickly. Forum.level1text.com. And what about ComfyUI? Well, you're gonna have to join us in the forum. LLM Scalar Omni is the path to get through to something that resembles a ComfyUI setup. And it's kind of similar. It's like the LLM scalar container with the older version of VLLM. Run a Docker image, you get a ComfyUI GUI. We want to pick preview method latent to RGB, and then these are the supported models. And so this is sort of a subset of what you might be expecting. But you can still do a lot with this. And so if you have a particularly interesting something that you've done with ComfyUI or a ComfyUI workflow that you want to show off, post it in the forum, and then we'll see if we can do image generation and do some other stuff like that. I'm going to keep tinkering with the LLM unsupported D-type stuff and try to make that a little bit more robust, but we'll see. It's like, oh, what should I do if I out of memory? Disable smart memory, but I've got 96 gigs to work with. Let's see how it goes. So, like, digging into this with some of the models, some of the squirreliness here is apparently like the chunked D types. I literally set that we were going to disable chunked prefill, and it says, okay, I'm going to use chunked prefill to a 48. Even if you set chunked prefill to 0, it accepts that, but then crashes. So, well, probably a bug in a container. Now, on the OneAPI side of things, I still get the warm and fuzzies for what Intel is trying to do with OneAPI. And generally, I've had a great experience with OneAPI in a sort of DIY context. Putting it plainly, having a vendor who wants you to use and build with that kind of a thing, where you can actually script and automate and just deploy stuff with Python, that's worth some points. And I like that, and I like where Intel's going with that. So, today, this video is about establishing the platform, what B60 is and what we can do with Battle Matrix, and the concept of what we're trying to accomplish here. It's first pass at a validated stack or validating the validated stack, I guess. And yeah, there's more benchmarks yet to do. But what workloads do you have? Like, I kind of want to turn this around, because what do you want to see me try to run on 4 24 gig GPUs that doesn't easily run on a single card? Do you care about throughput and latency, long context concurrency, tensor parallelism 4? Do you want diffusion, video, RAG pipelines, OCR, something multimodal, or something totally cursed that only this community would like to try? Yeah, maybe. I mean, it's sort of fun to experiment with. Docker, it's sort of fun. For AI and AI ideas, drop your workload ideas below, or hit me up in the forum and let's discuss something reproducible, containerized, scriptable, something I can easily run. Because the only way we figure out where B60 actually stacks up and where it actually belongs is to try to actually do something useful with it. And that is you in the community. What useful thing are you trying to do with AI? What do you want to see me try to run? Because I know that like HA proxy and that kind of stuff we can do. We can split loads. We can move these GPUs into another machine and, have 2 GPUs in this machine, 2 GPUs in that machine, and do some like network stuff. Like, there's a lot of fun things that we could do. But overall, for the testing that I was able to do, the performance is pretty solid, especially if you consider performance per watt and where they are with the VRAM. If Intel can scale this up, this will be really good. Architecturally, if you look at like Gaudi 2 and Gaudi 3 and like what Intel is doing on the enterprise side, they've got a little bit of the same kind of a problem that AMD has, which is that like RDNA and CDNA are not at all the same thing. And Intel basically has the same problem. And how Intel is going to solve that problem is nowhere near the forefront as much as on the AMD side. And then meanwhile, NVIDIA is just off in the background doing NVIDIA things. But still, for inferencing and how accessible this is and the costs. Intel is uncharacteristically aggressive with the costs here, impressively so. So this is a very promising platform, and it has a lot of really interesting aspects to it, but there is more science to be done. I'm Wilderness Level 1. It's been a quick look at Battle Matrix, the B64 GPU configuration. We're gonna run some more stuff, so engage. All right, I'm signing out, and I'll see you in the Level 1 forums, where I will be engaging with those of you that chose to engage. Battle Matrix!